All right, everyone. This is the test review 3 session, and first of all, we would be starting with basic differentiation, and then we'll make our way up from that. And let me change the screen to my tablet. All right, so everybody can see my tablet, right? Hopefully. Okay, then. Basic differentiation, we all know that if we have a number x, right, and it has the power n, then if I want to differentiate it or derivate it, the power goes down and the power reduces by 1. We all know that, right? Okay. Now, this is simple stuff. This is the basic building blocks of our differentiation. Now, let's quickly look into chain rule, what chain rule is. So, let's see, let's pick a let me just make something. Okay, sine of x squared whole squared. Now, the way chain rule works is that the way I personally perceive it as is looking it from the outside and then zooming it in. Now, this thing, if we look at as something, it is just some expression squared, right? Basically, what we do when we have x squared, we bring the power down and reduce by 1. And that is exactly what we are going to think. We are going to think step by step. So, this as a whole is just some expression squared. So, let me bring the power down and reduce whatever that was inside. I don't care what inside was yet, and reduce it by 1. Now, multiply. Let's go inside. Now, we are considering this. What is this? This is just some sine function, right? And what's the derivative of sine function? If anyone can quickly tell me. Cosine, perfect. So the derivative of sine is cosine. Now I don't care what's inside yet. Okay, I'm looking at this. So this is gonna be cosine, whatever was inside. Now we will zoom even further. We'll look at this. Okay, what is this? This is x squared, and we know the derivative of x squared is 2x. Now we can go further. If we just look at the x, the derivative of x is 1, but because it's just 1, we don't write it. And this is our chain rule. Hopefully everybody knows it. If you didn't know it, this is how you do it. All right. There are some basic derivative rules, the differentiation rules that you need to know. For like log differentiation, if I have ln of x, natural log of x, it becomes 1 over x if I differentiate it. Okay. If I have log of x squared, I'm again going to use my chain rule. So this is just some log function, right? The differentiation of log is 1 over something that was inside. So 1 over something that was inside times what was actually inside. It was x squared, so 2x. This is how it actually works. And we are just going to simplify it 1 over x. Alright, let me look at my agenda. Next thing is, alright, first of all, is everybody clear with chain rule? Alright, perfect. After this, we have some trigonometric functions: sine, cosine, tangent, and cosecant, secant, and cotangent. Now, a trick I have for this, to memorize this, is that the things that start with c will always have a negative derivative. Okay, doesn't apply to antiderivatives, just the derivative. The stuff that starts with c leads to a negative thing. Sine leads to cosine. Cosine leads to negative sine. Tangent leads to secant square x. Let me just write x really quickly. Alright, cosecant. Cosecant was, if I correctly remember, minus cosecant x cot x. Let me double check that. Cosecant x derivative. Yeah. Alright. Secant x is my cotangent. Secant x is net tangent x, something like that. Let me double check it. Secant x. Yeah, secant x tan x. X tan x. And now cotangent is it has a negative number, so it's gonna be negative cosecant square x. All right. Are we familiar with these now? Okay. Let's move forward. Now I'm gonna skip all the test 2 and stuff like that because that's in the past and we are gonna explore test 3 for now. So now I'm gonna switch back to my worksheet. Give me 1 second. Alright. So over here, let's look at this. And let me bring my uh-oh. Let me bring my tablet. Yeah, perfect. Alright, so over here we're gonna start with well, this is critical numbers increasing decreasing. Let me first tell you guys how to find the absolute minimum maximum and stuff like that. Alright, so over here this is basically possible because of two or three steps that I have that involves differentiation. Okay, now let's say we take an expression something like x squared plus 2x minus 1, and I want to find the absolute max and min of it. And it's let me actually take a question from the worksheet for that. Alright. Alright, let me take 4x cubed minus 6x squared minus 144x. Wait, whoa. Somebody's mic is on and it's very loud. Okay, perfect. Thank you so much. Okay, let's say hypothetically we have to derivate this. I mean, find the absolute max and min. So how it used to work is that, let's say this was the graph of it, and we have a line going like this. So what does these represent? What's the value of slope over here? Zero, right? And what does my first derivative tell me? The value of the slope, right? So that's why I'm gonna differentiate it. So derivating this becomes f dash x equals 12x squared minus 12x minus 144. Now, why do I set it equal to 0? Because I want to find the points when my slope is 0. So keeping this over here, I will first take 12, I will factor out 12, x minus 12 equals 0. Alright, I mean 12, if I divide by 12 on both sides, it becomes this anyways. So now I need to just factor them out. I can find two numbers. Alright, will 4 and 3 work? Yes, they will. So x square minus 4x plus 3x minus 12 equals 0. And I will take this common, x minus 4 plus 3, x minus 4 equals 0. And factoring both of these out, this becomes x minus 4 and x plus 3 equals 0. Now, the numbers I get from here, 4 and minus 3, these are called my critical points. Okay? There are two ways to find critical points. One is equating the top equal to 0 and the DNEs, which is basically, let's say we had a function on the bottom let's say we had something like, not over here, something like we differentiated and we had x minus 1 over here. Now you can think of it as setting the top equal to 0 and setting the bottom equal to 0. When we set the top equal to 0, we get 4 and negative 3. Those are my two critical points. And if I set my bottom equal to 0, I get, well, let's say if I got x minus 1, if that was the case, then 1 would also be my critical point. But in this case, we don't have it, so we'll remove it for now. So now, these are my points of interest. Earlier, to find the absolute max and min, what used to happen was that you were given a period in which you had to test these values, you had to test the endpoints and these values itself. And you would get basically all the values of all of those, and the highest one would be your absolute max and the lowest one would be your absolute min. Over here, we are trying to find the local min and local max. So for that, what we have to do is that we draw a number line and we put on our critical points. Okay? Now I'm gonna take this equation that I had over here, or the most factored equation. I'm gonna put that over here. X minus 4 and x minus 3, x plus 3 equal to 0. Okay, so what are we doing right now? Right now, we are trying to find the increasing, decreasing and local max and min. Okay, we are starting with our test 3 review. Let me quickly show you this. So right now we are over here, we are trying to find the critical number and increasing, decreasing and the first derivative test. We are on the first derivative test right now. Alright, let me switch back. Now, the way to find the to find the local min and max, we need to find the increasing and decreasing periods. So for that, you have this number line, right? This is required for us to do the first derivative test. Now, pick a number smaller than negative 3. We are going to test for this region. If let's say I pick negative 4. Put negative 4 over here. I'm not interested what the what the magnitude would be, but I want to know what the sign of this factor here would become if I plug in negative 4. So if I plug in negative 4 over here, this will become negative, and this over here will also become negative. Negative times negative is positive. So this region over here becomes positive. Now, between negative 3 and negative 4, let me pick a number. How about I pick an easy number, 0. So I'm going to pick 0 and I'm going to put it in there. So if I plug in 0 over here, I get a negative value. 0 minus 4 is negative. And if I plug in 0 over here, I get positive. Now, negative times positive is negative. Now, let's pick a number bigger than 4. It can be 10, 20, 30, 1 billion. Just has to be bigger than 4. Let's say I pick like 10. Now, if I plug in 10 over here, this becomes positive. This becomes positive. Positive times positive is positive. Now, these are the regions of increasing, decreasing and increasing again. The positive regions are when my graph increases. The negative region is when it decreases. And the positive region is when it increases back up again. Wow, I didn't expect it to be. I randomly drew the graph. I didn't know that it would mimic this. But that's nice. Alright. Let me copy this down over here. Alright, so now, as you can see over here, we have positive, right? Increasing. So, first the graph has to increase and then it will decrease. What does that look like? That looks like a hill, right? That means this point is a local max. Okay, first it increases, then it decreases. Over here, when we look at this value, first it decreases over here and then it increases, going like this. So this would be a local minimum. Local min and local max is basically, you can think of it as when the graph reaches a certain maximum point and basically changes its direction or something like that. Okay, so this was the local min and local max. A shortcut I have for this is when you reach this point, let's say you don't know the local mix min and max yet. First of all, these values need to be different. They need to be negative positive or positive negative. If it's positive positive, that just means that the graph is increasing. So if we look over here, we look at this number, the increasing and decreasing is determined by the value on the left. If it's positive, then this would be local max. If it is negative, then this would be local min. Okay? Alright, so that was the first derivative test. Now, let's move to concavity or the second derivative test. Is everybody clear with the first derivative test? Okay, perfect. Now, let's move to the second derivative test. So I would pick off where I left over here. This is my first derivative. Over here, let me pick this up and copy this down. I'm going slightly fast because I want to make sure that we have enough time for everything, because I don't want to miss anything. Okay, now somebody's mic is open. If well, this platform doesn't really let me. Okay, perfect. Thank you so much. It doesn't really show me whose mic is on, so I can't really figure out. Alright. So now, this was my first derivative over here. Now, to get to my second derivative, to find the concavity, I have to go to my second derivative. So let's take a derivative of this again. So this would be f dash dash x equals, this becomes 24x minus 12. Alright. Now, what is concavity? Let's first discuss that. Let's say I have this graph over here and I have something like this. Concavity is that region, it basically tells us the shape of the graph. So if we look from here to here, it is concave down, it's like this. And then it starts again to change its shape and it again becomes like this again. It becomes this shape again. So concavity is the shape of the graph. Increasing, decreasing, maximum, minimum, that was for like these points. And basically these regions, when it's increasing, when it's decreasing, those were those regions. Concavity is the shape of the graph. And when the graph changes, it will have this point where basically the shape of the graph changes. This point is called point of inflection. All right. So if we like zoom in over here, the graph is all right. So the graph is slightly like this over here, and at this point it starts to become slightly like of this shape. All right. Let me see if I've shared the correct thing. Okay, good. Now, if we go over here, to find the points of inflection, I basically need to equate my second derivative equal to 0. So let's equate this equal to 0. 24x minus 12 equals 0. Let me factor out 12. This becomes 2x minus 1 equals 0. Let me verify if my differentiation is going correct. 12, yep, 12. Alright, perfect, it's good. Now, I can divide by 12 on both sides. It reduces to this. adding 1 on both sides, and dividing by 2. So my point of inflection becomes x equals 1 over 2. So over here, or not basically, like whenever the graph was changing, let's say this was 1 over 2. At this point, my graph stops being like this and changes to be like this. Now, how to determine what shape of my graph is? So similarly to the increasing and decreasing, we have another number line test over here. So I draw the number line and I have 1 over 2. Now let's pick a number smaller than 1 over 2. Let's pick 0. So if I plug in 0 over here, which is 12 times 2x minus 1 equals 0. If I plug in 0 over here, I get a negative number. So this becomes negative over here. If I plug a number bigger than half, let's say 5,000 over here, this is like 10,000 minus 1, which is like a positive number. So this becomes positive. Now, the regions where it's negative, it will be concave down. The regions where it's positive, it will be concave up. Now, what does concave down look like? Concave down looks like this. Concave up looks like this. As we can see over here, in this region, it's concave down. And in this region, it's concave up. Alright, this was basically increasing, decreasing, maximum, minimum, points of inflection, and concave down and concave up. Does anyone have any doubts regarding this? It's basically, both of them are the same things, but they happen to be the same thing, and they lead us to like different answers, like us to determine different things about our graph. Right now, what test 3 is, like the first part of it, these inflections and everything and identifying the graph, is everything that you have learned till now, using that to actually make that graph. Some of the professors I know, they won't make you make the graph, but they would make you go through the steps like finding the concavity and everything. So you need to know these. Alright, so let's move to the next portions. Let's look for if we missed anything. Okay, so we covered the decreasing, increasing, and alright, we covered critical points, concave up, concave down, concavity test. Alright, second derivative test. This is one of the other tests. So let me explain this to you. So let's say we again take this graph. Copy this and paste it over here. Now, let's say I pick a point of my critical point. This was my critical point and this was my critical point. And they were negative 3 and 4. So let's say this was negative 3 and this was 4. Now what does the second derivative test say? If my if I plug these numbers, negative 3 and 4, into my second derivative, which is in my first derivative, which is basically this over here. Let me copy this down. Over here, and if I plug it into this over here, come on, paste. Alright, so if I plug it in over here, and so these over here, these numbers should give me 0 when I plug it over here, because it's the slope. This equation tells me the slope of the graph. The first derivative always tells me the slope of the graph. So if I plug it over here, it will give me 0. And if I plug it over here in this equation, it gives me whether the graph is concave up or concave down. So if I plug it over here in this one and it gives me 0, and I plug it in over here and its value is bigger than 0, then it should have a local minimum. So it should be a case like over here. So if I plug in it in over here, the first derivative would give me a 0 because it tells me the slope, and if I plug it in over here, this would give me a concave up result, which means that the shape of this region is like this, and at this point the slope is 0. So definitely this point is a local minimum. Similarly over here, this point has to be 0. If I plug it in over in the first derivative, this point has to be 0. That means my slope is 0. And in the second derivative, if I plug it into the second derivative and it gives me a positive, if it gives me a negative value, that means the graph is concave down. That means it has a local maximum over here. The shape of the graph is like this, concave down, and at this point it's giving me 0. So definitely this point would be a local maximum. And if they both are equal to 0, then the test is inconclusive, doesn't really tell about what that is. So if we want, we can quickly plug it in over here. So if I plug it in the first one, let's plug in 4. So f dash x would f dash of 4 would give me 12 times 4 squared minus 12 times 4 minus 144. So 12 times 16 minus 12 times 4, which is 48, minus 144. And let me pull up my calculator really quickly. I didn't forget it at my home. Perfect. Okay. So 12 times 16 is 192 minus 48 minus 144, which is 0. Perfect. This proves that this point is on the part of the slope when the slope is 0. If I plug it into the second part, 24x minus 12, f dash dash x equals over here, and if I plug in 4 over here, this becomes 24 times 4 minus 12. So 24 times 4 is, that's 96. 96 minus 12, that is 84, which is a positive result. That means at this point it should be like concave up, and indeed at 4 we can see that the shape is concave up, and it is at a local minimum. It is at a slope 0, so it's definitely local minimum. Alright, so this was 4.3. Do we have any questions regarding 4.3 before I move on to 4.4? You set it equal to 0. Set what equal to 0, Fatma? How do you know when it's considered a critical point or when it's not? Good question. So, after you have, well, earlier, so you might get confused with this. And earlier we used to find the absolute min and max, and we used to rule out possible critical points and the ones that we do not take in because we had the bounds. But over here we do not have any bounds. So after the first derivative test, whatever you get, you basically set the top equal to 0 and the bottom equal to 0. The top equal to 0, you will get the roots, and the bottom is basically the DNEs. So all of those numbers would be your critical points. Alright. How do you know? Okay, but I mentioned that we use the second derivative of concavity and first for increasing, decreasing, original for min, max. Max and min. Basically, so original for max and min, which was in our previous concept when we were trying to find the absolute min and absolute max. Right now, we won't be really, well, we would be later on when we are trying to graph the thing. Then we would be putting it in the original equation to find the 2 points. But basically, right now we are not interested in finding the absolute min and max. We are trying to form the overall shape of the graph. Also earlier when you were trying to find the concavity, you would just plug in the numbers either smaller or bigger than the point of the inflection. Yeah, right. So over here, it's pretty similar to the first test that we have. If the numbers would be negative, the numbers would be smaller than half over here, and a number that is bigger than half over here. If it's negative, then it's concave down. If it's positive, then it's concave up. So they both are basically, they look similar, so they're easier to remember. All right. So with that, should we move on to L'Hopital rule? Perfect. All right. L'Hopital rule. Some people call it L'Hospital's rule. Some people call it L'Hopital rule. I call it L'Hopital rule. It's just preference. People just fight over it. All right. So L'Hopital rule, what it will boil down to ultimately is knowing this fact that when you have a limit x goes to something and you get the form 0 over 0, when you plug the thing in you get the form 0 over 0 or infinite over infinite, then you can derive it. Alright. So when you have this, you can basically derivate the top and differentiate the top, or derivate the top and bottom, and then you would do it. So let me explain it how it works. Let's say we have something like fx over g of x, and it goes from limit of x to something. And let's say when I plug in that limit, let's say x goes to 0, I get 0 over 0 as my answer, or infinite over infinite. These are undeterminate forms. We don't know what 0 over 0 or infinite over infinite is. But L'Hopital came over with this rule that if you ever get this, then you can derivate the top and derivate the bottom and keep them the way they were. So it would be f dash x over g dash x. This is not product rule. I mean quotient rule. This is entirely different. So when we get over here, we will again plug in the 0 till we find a conclusive answer. Either it's infinite, 0, negative infinite, something like that. Usually your answers would end up in like 0, 1s, negative infinite, stuff like that. Alright, let's pick an example because we learn better through examples. Let me pull on the tab and pick a question. So let's take let's take this question. Okay, so a limit of x goes to 0 sine x minus x plus 3x squared over 2x squared. Now my first order of business every time in any limit is to find the top, and is to basically plug in the number. So if I plug in the number sine of 0 minus 0 plus 3 of 0 squared over 2 0 squared, this basically becomes sine of 0 is 0, right? You need to know the unit circle values now that you're in Calc 1. It's basically it's assumed that you guys would know it. Alright, 0 minus 0 plus 3 times 0, which is 0, over 2 times 0, which is 0, which is 0 over 0 form. You need to always, always, always ensure that you have either 0 over 0 or infinite over infinite. If you have any other form, you need to work on it, which we will learn in a few moments. Alright, so now that it is 0 over 0, so you can write it on the sheet, which basically helps the teacher to know that you have correctly identified it. You can write because it is in the form 0 over 0, we can use L'Hopital's rule. And what does it say? So I have my original equation over here, right? Let me differentiate the top part, which is basically, and the limit still needs to be there. So the derivative of sine x is cos x minus the derivative of x is 1. The derivative of 3x squared is 6x over the derivative of 2x squared is 4x. Now my job is to again plug in the 0. So now plugging in the 0 again, I get cos of 0 minus 1 plus 6 times 0 over 4 times 0. So cos of 0 is 1 minus 1 plus 6 times 0 is 0 over 0. Again becomes 0 over 0. You can write the thing again. Because this is in the 0 over 0 form, we can use the L'Hopital's rule. This just makes the exam very presentable, and your examiner would appreciate you. Now, because this is in the 0 over 0 form, we can use the L'Hopital rule again on this. We will keep doing it until we have a decisive answer, until we have a conclusive answer. So, using the L'Hopital rule, what does it say? Derivative of top, keep it on the top. Derivative of bottom, keep it on the bottom, and test it again. So, cos, the derivative of cosine is negative sine x. The derivative of 1 is 0, and the derivative of 6x is 6. Over the derivative of 4x is just 4. Now, let's plug in the 0 again. Minus sine of 0 plus 6 over 4. What's sine of 0? It is 0. So 0 plus 6 over 4, we get 6 over 4, which is 3 over 2. And this would be my final answer. This is a conclusive answer. I can conclude this. This doesn't leave me to any indeterminate type. So this would be my answer of the question. Did everybody understand that? Perfect. Because this is the bones, or this is the backbone of L'Hopital rule. It will always lead back to this. The other forms would be us adjusting our question to make it back into 0 over 0 or infinite over infinite forms. Alright, let's move on to the other forms over here. Let me pull up my sheet. So let's go over here. L'Hopital rule. Okay. So now that we have this one done, let's go to our second form, which is infinite times 0. So we would have basically 3 types of forms. The one we already did, infinite over infinite, or 0 over 0. That's my first type. What do I use? L'Hopital rule. Next, my form is 0 times infinity. It is not 0, it is not infinity. It is an undeterminate type. we don't know what the answer of that would be. That's why we work our way around and use the L'Hopital rule to find that. The next type would be infinite minus infinite. No, it is not zero. Infinite minus infinite doesn't really make any sense. It's such a big number, we don't know what would happen. So we would make our way around even that over there. And the fourth forms are the ones in the power 0 over 0, 0 to the power 0, infinite to the power 0, 1 to the power infinite. Infinity squared is just infinite. That's one of the funny things that happened in my calculus class in spring semester. Don't write infinite square in infinite times infinite as infinite square. It's just infinite. It's a bigger number. All right. Now before beginning, let's know some helpful limits. The limit of x of limit 0 is negative infinity. So you know that. Alright, it's in the correct form. The graph of a log function is like this. This is at, I believe, at e. So if it's a natural log function, this is the log of e is 1. And it starts from negative infinity. So if we get very close to 0, it goes to negative infinity. Similarly, e to the power x, if we plug in infinite over here, it becomes infinite. If we plug in negative infinite, which is basically limit of x goes to negative infinity to the power x, this becomes e to the power negative infinity, which is 1 over e to the power infinity, 1 over a very, very large number. That is basically 0. Alright, and this basically explains what we knew about the horizontal asymptote. If the top is bigger, then if the bottom is bigger power, then it becomes 0. If they are the same, then the ratio of coefficients. And if the top is more, then it goes to either positive or negative infinity. Okay, let's come back to our 0 times infinite question. In this, I would have something like, let me change to my tab. I would have fx times gx. These are just two functions, and one of them, if I plug in x, one of them would become 0 and one of them would become infinite. How to counter this? So I said this is, let's say fx goes to 0 and gx will go to infinite. So for this, what I do is that I make an intelligent guess and I flip one of them. So this becomes, let's say I flip fx, okay? So gx over 1 over fx. They are the same thing. If I flip it back, it goes over there. This, recognize that this and this mean the same thing. Now, as I said, fx went to 0 and gx went to infinite. So gx was going to infinite and fx was going to 0. What is 1 over 0? It is infinite. So infinite over infinite. We are back in the L'Hopital form. Now we can use the L'Hopital rule again. Let's complete this with a example. Tab plus. Alright. Let's pick an example over here. Infinite, 0 times infinite. So let's pick. Let's pick f. So f is limit of x goes to 3 from the right, x minus 3 cubed log of x minus 3. Now, generally, when we have, so let me take this question first. So we plug in 0 every time until we get an answer. And what if we don't get a 0 over 0 form? First time we check for the indeterminate form or to use the L'Hopital's rule. So your question is that, let's say we do not get the 0 over 0 form or the infinite over infinite form. Well, the indeterminate forms would be something like these. If it's not an indeterminate form, then it's basically the answer. We are trying to find a conclusive answer. We don't plug in, actually we don't plug in 0, we plug in the limit, whatever we were given. In this case, it was 0. Alright, let's move on with our question. So as you can see over here, we are plugging in 3. All right. So let's plug in. So our first order of business is to plug in stuff. So 3 minus 3 to the power 3 log of 3 minus 3. So this becomes 0 cubed log of 0, which is 0 times log of 0. Now, what is log of 0? Log of 0 is negative infinity. This becomes 0 times negative infinity, which is basically negative 0 times infinity, or whatever. Basically, it's in that form. It's in this form. So, in this form, so what if our limit was infinity? We plug in that. Yeah. Let's say I have something like limit of x goes to infinite and I have 1 over x. If I plug that in, 1 over infinite, 1 over a very large number becomes 0. Plugging in infinite is the exact thing we do to find the asymptote, the horizontal asymptote. Okay? Okay, Srinidhi? Perfect. Now, let's continue with this. So, let's make an intelligent guess with this. Logs are very are are kind of messy to deal with. So let's take the polynomial on the bottom. So can I write this as log of x minus 3 over x minus 3 with a negative power? When I reciprocate something, it becomes the negative power, right? Limit of x goes to 3 plus, which means 3 from the right. All right, now that I have this in this form, let me test it again. So log of 0 over 0, or basically let's do 3 minus 3 with like this. So it could be written like log of 0 1 over 3 minus 3 with a positive power means the same thing. So this becomes infinite, and this thing over here, this would become 1 over 0, which is infinite again. So infinite over infinite. Now we can use the L'Hopital rule on this. This over here, we can use L'Hopital rule. Am I maximized? Let me maximize my tablet. Alright. Alright, now let me take this again. Log of x goes to 3 from the right. Log of x minus 3 over x minus 3 with the power of negative 3. Now let's use L'Hopital rule. Basically, because we got infinite over infinite, we can now use the L'Hopital rule. Always write that whenever you are using L'Hopital rule, you need a solid reason to use L'Hopital rule. You cannot willy-nilly just plug in L'Hopital rule anywhere, okay? Now, the derivative of log of x minus 3. So log of x minus 3. Let me use the chain rule over here. So log of x, or log of something. So 1 over something that was inside. Now what was actually inside? X minus 3 was the derivative of x minus 3, which is just 1. So we don't really write it. So let me write this as 1 over x minus 3 over. Now this would be bring the power down, minus 3, x minus 3. Then I'm using the chain rule again. Over here, this is something raised to the power minus 3. Okay, let me bring the power of that something down and decrease the power by 1 times. Now, what's actually in the inside? It's x minus 3. So, the derivative of x minus 3 is just 1, so we don't really write it. Now, let me do a little bit of reshuffling. So, x minus 3 to the power minus 1 over minus 3, x minus 3 to the power minus 4. Limit of x goes to 3 from the right. Now I can take this thing on the top, not minus 3. I can take this thing to the top and the power would become positive. I can take this thing to the bottom and the power of that thing would become positive again. So this is the limit of x goes to 3 from the right. X minus 3 with the power 4. On the bottom, this thing remains over here because it doesn't have a negative power, and I can bring the x minus 3 down. Now what do I observe here? This and this and this, they are the exactly same thing. I can take them out, and this would be a factor of this would be reduced. So this would be a limit of x goes to 3 from the right, and if I cancel this over here, this becomes 3. So x minus 3 to the power 3 over negative 3. Now that I am to the simplest form that I can reduce it to, let me plug in the 3 again. So 3 minus 3 to the power 3 over negative 3. This becomes 0 to the power over negative 3, which is just 0. And this is a conclusive answer. I can stop over here. This is my final answer. Alright, so let's recap. What did we do? We first plugged in 0 and we found that it's 0 times infinity or 0 times minus infinity, same thing. So with that, I know I have to use the method in which I have to reciprocate. So I made an intelligent guess and I reciprocated the polynomial over here, and I plugged in the 0 again to re-verify, and I got infinite over infinite. Because we have infinite over infinite, we can use L'Hopital's rule. So using the L'Hopital's rule, I got over here and I reshuffled stuff around, did a bit of algebra, and I got to this point. Then I plugged in 3 again and I got the answer as 0, and I can stop over here. This is my final answer. Does anyone have any doubts regarding this method? Because we need to be crystal clear, because as we move forward, we would be recursively going back on the method. So the next method can possibly use this method and L'Hopital's rule. Alright. Thumbs up, everybody. How does x to the power 3 plus affect this entire problem compared it to being x equals 3? How does x 3 from the right? Okay, why did we have x to the power 3 from the right? Now this has nothing to do with L'Hopital's rule. It has to do with basically what are we doing in math. So if we look over here, we have a log, right? And we are passing the thing from the right. Let's say I pass in a thing from the right. So this would become log of a slightly bigger than 3 minus 3. So it would be log of 0.00000000000 goes to infinity 1, right? A very tiny number. So it would lead to me somewhere over here going to infinity. So it leads to me to negative infinity. Now, that is a conclusive answer. We can kind of say that it's like it can happen. Like it can go to negative infinity. We can say that. But let's take a number from the left. 3 from the left. So this would be 3 from the left minus 3. So it would be 2.9999 minus 3. A very small negative number. But look over here in the graph. Does it ever cross the y-axis? Does it ever go to the negative side? It never crosses this. It always comes very close to 0, but never goes over here in this region. So that's why if we plug in 3 from the left, it would lead me here plugging in a negative number over here in the log, which doesn't make any sense. Now, because from the limit from the left, it doesn't exist, because it doesn't exist from the left, and it kind of exists from the right, we cannot conclude that the limit exists at 3. So that's why we are testing it from the right, because it doesn't exist from the middle, because it doesn't exist from the left. Alright? Alright, glad you got that. Somebody asked me this in the tutoring sessions I do. Alright. So should we move forward to the next step, to the next part of our methods? Okay, let's go. Now, my next is infinite minus infinite. In this, I would have to either take the denominator common if they are in like fractions, let's say x over 2 or minus like 5x square over x, something like that, a to the power, something like that. I would have to take the denominators common, or let's say I have something like log of x minus x. I have to artificially take them into a fraction so that I can put them into a form like that. So let's say it was this. I will go over both of those forms. So let me first go to a simpler form and let me take an example, because this one can only be taught with an example. So let's take and I would give 15 more minutes to L'Hopital's rule because we would need to move forward. So let's move forward. So let's do this quickly. However, we cannot lessen the quality of the lecture. So let's do this. Okay. Which one should we pick? Let's pick n. Now, n has a typo in it. It's 1 over log of x minus 1 over x minus 1. I did point this out to Dr. Miller. I don't know why. Maybe I have the wrong version of it or something. But this is a negative, because if it wasn't negative, it would be infinite plus infinite, which is infinite, which we can determine. All right. Now over here, what's my first thing to do? My first order of business, it's to plug my limit in. So plugging my limit in, I get log of 1 minus 1 over 1 minus 1. Log of 1 is 0. Log 1 to the any damn base is 0. I learned that in my 11th grade back in India. My teacher my teacher in my class, they told me log 1 to the any damn base is 0. Always remember that. So this becomes 0. Minus 1 over 1 minus 1 is 0. So this becomes infinite minus infinite. This is the form that we are talking about. So infinite minus infinite. In this, what did I talk about? I need to either artificially take them common, or if they are in fractions, I can just take their basis common. So this would be, if I combine the denominators, this, or let me just quickly do that. So I need to have the denominators log of x times x minus 1. I need to have both of those denominators. So this part is missing x minus 1 over here, x minus 1 over here. So I would have x minus 1 over here minus, and this part is missing log over here, log over here. This would be minus log of natural log of x. Now let's simplify this further. So this would become x minus 1 minus log of x over log of x. Let me just keep it like this. Alright. And let me plug in the limit again. Now notice over here too, we have 1 from the right. If we had 1 from the left, well, actually we could have one from the left. Maybe. I don't know. Alright. We have 1 from the right over here. This session is indeed recorded. Alright. So now let's plug in the 1 over here. 1 minus log of 1 over log of 1 and x minus 1. I mean 1 minus 1. So this becomes 0 minus log 1 to the any damn base is 0 over 0 times 0, which is 0 over 0. And 0 over 0 is a L'Hopital's form. So we will write over here, because it is of the form 0 over 0, we can now use the L'Hopital's rule. Never ever use it without that explanation. Alright, now let's take this again. We duplicate it and not good. We duplicate it and put this over here. Okay. Cannot think of a reason for 1 from the right in this situation. Alright. Over here, now we can take the derivative of the top using L'Hopital rule, the derivative of the top and the derivative of the bottom. So this would be limit of x goes to 1 from the right. So derivative of x is just 1, derivative of log is 1 over x minus 1 over x. Oh no, I took a hard one. The algebra for this is a bit hard. Okay, no worries. On the bottom we will use the product rule. So it would be the derivative of the first thing, so 1 over x, leave the second alone, minus derivative of the second thing, so it would be x minus 1 derivative is just 1 times log of x. So this would become x minus 1 over x, and on the bottom let me do a bit of cleaning up, so it would be minus log of x, well, x times log of x over x. And somebody's mic, there's some songs playing through somebody's mics. Alright, now x minus 1 over I would again make an announcement to mute your mics. Your voice is coming through the meeting. That's right. All right. No, I'm also recording it. All right. All right. Okay, never mind. This becomes this over here. So now all right. Now that we are past that, this thing doesn't really give me an option to mute everybody. Yeah, it doesn't. Okay, never mind. We'll try to move forward. Okay, so now that we are over here, let's plug in the one again over here. This would be 1 minus 1 and which upon 1 minus 1 minus 1 times log of 1. So this becomes 0 over 1 minus 1 is 0 minus log of 1 to the any base is 0. So this becomes the 0 over 0 form again. So now let's take the derivative of this thing again. And don't worry, nobody's voice goes through the recording. Okay, this if the person who is on the call, they can hear me, your mic is unmuted and we can hear you. Okay, then let's move forward. Okay, now this, because this is in the 0 over 0 form, we can differentiate it again. So x minus 1, the derivative of that is 1, which is just 1, and on the bottom the derivative of x is 1 minus 0, and we have to use the product rule again over here, which is basically the product derivative of the first one, log of 0, plus the derivative of the second one, and leave the first one alone, 1 over x times x, which is just log of x plus 1. 1 minus 0 minus log of x plus 1. Alright, now this would be 1 over 1 minus log of x plus 1. Now this basically becomes, and we are plugging a limit of x goes to 1. This becomes 1 over, let me pull up a new sheet, 1 over 1 minus log of 1 and to the any base is 0, 1 minus 1, which is 1 over 0, which is infinite. Now, infinite is a conclusive answer. So we can conclude that this thing goes to infinite. Alright? Wait, let me see actually. Let me check the answer of this question. And oh wait, it leads to 1 over 2. Hold on. Let me quickly see where we went wrong. One over x or minus 1. Wait, this is supposed to be a plus, I think. Is it? 1 over x. Yeah. See, a plus ruins everything. So if this was plus, this was also plus. And where did this x come from? It did come from here. Okay. And it should be plus over here. And if we plug in 1 in this, 1 minus 1 over 0 plus 0, okay. Plus over here. And we took the derivative of that, 1 over 1 minus plus. This becomes plus. There we go. 1 plus 1, and this becomes 1 over 2. Wow. Alright. So the answer is 1 over 2. And even if it was infinite, it was a conclusive answer. Alright. Now, let me show you just another form which is very important, log of x minus x. And over here what I'm going to do is that I'm going to artificially take a fraction. So let me multiply and divide by x on the log. I can do that. I can take the x common, so log of x over x minus 1. Now limit of x goes to, the limit went to infinite actually. X goes to negative infinity, plus positive infinity. Now over here what I'm going to do is that I'm going to plug in my limit. Well, if I plug in my limit over it would be just infinite minus infinite, and I wouldn't know what to do. And let's just plug in my infinite over here. So this would be infinite over, infinite times log of infinite over infinite minus 1. Now the problematic thing over here is this part, so let's zoom into that part. Limit log of infinite, so this would be log of x over x, and its limit still goes to infinite. If I plug in the limit, it becomes infinite over infinite. So that means I can use the L'Hopital's rule. So over here this would be 1 over x over 1. The derivative of this is 1 over x, derivative of this is 1. So this becomes 1 over x. Now limit of x goes to infinite. So this is 1 over a very big number, 1 divided by a very big number, which is basically 0. So I know that now this part is 0. So this part becomes 0. So I can conclude that this becomes infinite times 0 minus 1, which is just negative infinity. Alright, BOD mass. First figure out what's on the inside, then figure out what's on the outside. So my answer here over here would be negative infinity. So are we clear with the infinite minus infinite property? Alright, I see the funny comments in the chat. It's alright. Accidents do happen. But are we clear with this? Perfect. Thank you so much. Alright, let's move forward then. Because time is of the essence. Is that how it's said? Sorry, I'm not from a native English country. That's how you say it, right? Alright. So the next part would be over here. Alright, the next and the final form we have is 0 to the power 0, anything to the raised to the power anything, basically. I mean, not anything. 0 to the power 0, infinite to the power 0, 1 to the power infinite. What's 1 to the power 0? Quickly, somebody tell me. 1. Perfect. Good job, guys. So only the indeterminate forms. So over here, what I will do is that, well, dealing with powers, we generally, I looked it up. Oh, nice. All right. So generally, when we are dealing with powers, stuff with powers, we always use logarithms. Logarithms are a very nice tool because of one of their properties. If we have log of, let's say, x squared, I can take this power down outside. 2 times log of x. Now these mean the same thing. I can use this property to my advantage, and this can be only explained with an example. Alright, let's pick an example. Let's pick J. Maybe J. Which one should I pick? Let's pick sin x to the power x. Alright. Switching my minds. Okay. Limit of x goes to 0 plus. Oh well, I would be too easy. Let me show you. Cos of x 1 over x. Now this is equal to something, some function, right? This is some function. I can equate it to y, like we did in logarithmic differentiation, right? Dude, I love logarithmic differentiation. Look, I love the logarithmic differentiation. It was just magical when I looked at it in the class. Like, it's such a messy thing, and it gets differentiated. It's so good, and that is what we are going to use over here. All right. So my first step over here, well, in generally, what my first step was plugging in the limit, right? So this would be cos of 0 to the power 1 over 0. So this is cos 0 is 1 and 1 over 0 is infinite, which is an indeterminate form. We don't know what's 1 times infinite times 1's. Yeah. All right. So now over here I have to use logarithmic difference, I mean logarithmic stuff. We can say that. Okay, now taking log on natural log on both sides. Log of y, and you have to, well, mathematically keep stuff inside the limits. So this would be limit of x goes to 0, doesn't really matter because it's a y variable on the left, so wouldn't really affect. So log of y, come on, log of y. Is my screen visible first of all? Let me switch it to the tab. Alright, so log of y equals limit of x goes to 0 log of cos x to the power of x. Now, what was my property of log? It brings the stuff down, and that's exactly what I'm going to use over here. Well, first on the left hand side, I can say that there is no x variable, so the limit doesn't really do anything. We can say that it's multiplied by x to the power 0 and plug into 0. Don't plug into 0. No, forget that. I'm introducing another paradox with that. Okay, now let's say that the limit on the left doesn't really do anything. So log of y equals limit of x goes to 0. Now bringing the power down, 1 over x times log of cos of x. Now let's plug in the 0 again. So this would become log of cos of 0 over 0. What's cos of 0? Cos of 0 is 1 over 0. Log of 1 is 0, 0. So becomes 0 over 0. Now, because it is of the form 0 over 0, therefore I can use L'Hopital's rule. Write that on your exam sheet. Your grader will bless you. Trust me. Okay. Now, over here, let me put that to the side. Let me put this to the side. So over here I basically have limit of x goes to 0. What should we write? You should write, because it is of the form 0 over 0, we can use L'Hopital rule. Sorry, my handwriting is not good. I'm a CS guy. I do more of typing. We can use L'Hopital rule. Write this whenever you encounter that, and then use the L'Hopital's rule. Okay? Alright, let me keep that on the side. Now, log of x log of cos x. No, so now because it's in the 0 over 0 form, this would be 1 over, no worries Samuel. So this would be log of something that was on the inside, log of log of something that was in this side, 1 over something, so 1 over cos x. Now what was actually on the inside? Cos of x. What's the derivative of cos of x? Sin x, or maybe, or let's no, it's negative sin x. Negative sin x over, what's the derivative of x? 1. So this becomes negative sin x over cos x. Don't forget the limits. X goes to 0. Now, sine over cos is basically tangent. This would be negative tangent x log the limit of x goes to 0. Don't forget we have a log of y on the left. Now, what's tan 0? Tan 0 is 0. So this becomes, if you plug in the limit, this becomes negative tan 0, which is just 0. We have natural log of y on the left. Now, we need to resolve this limit before answering our question. So this would basically become, log of y is basically log y with the base e equals 0. They're the same thing, natural log is that. Now, this would go over there. This would become y equals e to the power 0, e to the power 0. 0 is 1. And this would be my final answer. Recap. First we plugged in the 0, you found it's 1 to the power infinite. After that, we because it's the power stuff, we took the logs on both sides, natural logs on both sides. After that, we used the property of log over here, brought the power down. After that, we plugged in the 0 again. It became the 0 over 0, 0 over 0 form. We wrote that because it is of the form 0 over 0, we can use the L'Hopital rule. Then we used the L'Hopital rule. We got this sine over cosine is tangent, which is over here, negative tangent. And then we plugged in the 0 again. Tangent of 0 is 0. So this becomes log of, and because do not forget we had a log of y on the left. So log of y equals 0, and which basically reduces to over here y equals 1. Are we 100% sure with that? Do we have any doubts? For sure. One over cosine x. This, yeah, this part. Alright, so we have log of cosine of x, right? So this was like, this is basically log of cosine of x over x, right? So I'm gonna use the L'Hopital rule over here. Log of cosine of x. So log of x is like basically 1 over x, right? 1 over something that was inside, log of cosine of x. So log of cosine of x, 1 over something that was inside. So 1 over something that was inside. Now, what is actually in the inside? Cosine of x. So I'm going to use the chain rule. Cosine of x. The derivative of cosine is negative sine. Basically, I'm differentiating log of cosine. Okay? Alright. So, are we good with this topic now? Alright, this is the end of L'Hopital rule. It isn't that bad. It just leads back to the original thing. Okay, now let's see what's next on our agenda. L'Hopital was one of the big things that we needed to cross. Alright, L'Hopital rule, bye-bye. I mean, not for you, for me. Oh, even I'm in calculus 2 right now. I use L'Hopital rule quite frequently. Not quite frequently. Basically, I encounter sometimes when I have to use it, and I get happy. Oh ho! I learned that in Calc 1. All right. Section 4.5 is constructing a graph. I believe. Yes, it is. So for this, basically what you will do is that you will use all the knowledge you have about that you have gathered till now, all the increasing, decreasing, intercepts, even, odd, horizontal asymptote, vertical asymptote, concavity, and local max, min, intervals of points of inflection, and use that to draw it onto a graph. Many teachers, many professors don't want you to actually draw the graph. They just want you to perform all of those operations, and they'll tell you, maybe, I mean, in my final exam, in my test 3, not in my final exam, in my test 3, my professor put it in the test like, what's the concavity of this point, what's the points of inflection. So this whole section, I can just explain it through like one question. Alright, let's pick a question for that. Let me put this on the bit to the left. Yep, alright. Let's look at this. Alright. Now, let's look at a question. And we want to find the, well, this is what we have done, L'Hopital rule. Alright, so section 4.5, yeah, right, it would be like this. Find the following for the given functions. Alright, which one do you guys want to do? Pick. 1, 2, or 3. 10 seconds. Otherwise, I'll pick a random one. One, two, three. Okay, perfect. Three. Guys, you gave me the dirtiest one. All right, no problem. It's okay. I still love you guys. All right, let's do this. Let me rearrange this. Put it like that. Whoa, that would be too small. Let me move this up. That should work. Yeah. All right, everybody can see that. Thank you, Jared. Okay, my first. So the steps have been given to me, and I need to follow that. I don't know if that would be given on the test. They should be, but I'm not saying anything. Okay, I'm just doing what the question says. Okay, finding the domain of the function. So the domain. How do I find the domain? The domain is okay. Let me first tell you guys what actually a domain is. Okay, does anyone wanna volunteer me explaining this thing? I need somebody on the voice. It's nothing. Trust me. Nothing to fear about. Just need to say yes and no. Come on, anyone. No, no, we are gonna start over with the domain thing. Okay. Are you gonna volunteer? Do you wanna volunteer just me explaining the thing? Alright, let me turn up the voice on my recording. Alright. Now, let's think of a function as a machine, okay? Alright? Bro, say yes.
Yes.
Alright. Let's think of function as a machine. Okay, let's think of it as a juicer. Alright? Come on, man. You have to say yes.
Okay. Okay.
Yeah?
Yes.
Alright. Now, in a juicer, can I put oranges through it?
Without. Sorry. Can you repeat that?
Can I put oranges through a juicer? Like I'm just making orange juice. Can I do that?
Yes.
Right? Can I put some grapes through it? It would work, right?
Yes.
It would make some sort of juice. Alright. How about some pomegranates? Would make pomegranate juice, right?
Yeah.
But can I put rocks through my juicer?
No.
No, right? There's no rocks juice. So that is what basically domain is. Domain is, thank you so much for participating. Uh,
Of
domain,
course.
i- domain is basically my set of all those numbers that work for my equation. Okay, that doesn't leave me to an answer that doesn't make any sense. So if I plugged in like oranges, give me orange juice. Plugged in grape, gave me some sort of juice. Plugged in pomegranate, gave me pom juice. Now, if I plugged in rocks, didn't give me any juice. It didn't lead me to any answer. So domain is the set of all those numbers which work for my equation, which I can actually put inside of my equation, and I can get a decisive answer. All right, now over here in the numerator, if I have a polynomial, I'm not really concerned about it, because in the numerator I can plug in any number, it would give me an answer. But in the denominator, okay, tell me what is the one number my denominator cannot be. Perfect. Thank you so much. My denominator cannot be 0. It would make it undefined. So that's why I find the roots of the bottom, the roots of the denominator, x square minus 4. So to find the roots of the denominator, I equate the denominator equal to 0, which is basically x square equals 2. And taking under root on both sides, I get plus and minus. Oh wait, 4. Yeah, which is plus and minus 2. So my numbers can be any of the my domain can be any of these numbers except plus and minus 2. The plus and minus 2 leads me to a vertical asymptote. So my domain is minus infinity to minus 2, union minus 2 to 2, union 2 to infinity. Alright. Did everybody get that? Perfect. Thanks for the enthusiastic yes. Alright. Finding the x and y intercepts. To find the x-intercept, okay, let's say I have a graph over here. What are intercepts? Intercept is when my graph crosses this, the y-axis and the x-axis, okay? These are my intercepts. Now, at my x-intercept, at this point, what is the value of y? 0, right? That is what I'm going to use to an advantage. At this point, the value of y is 0 and my function was x square over x square minus 4, y equals 0, and my y was 0 at an x-intercept. So let me take that to my advantage. 0 equals x squared over x squared minus 4. Okay, if I multiply by x squared minus 4, it becomes 0 equals x squared and x equals 0. So my x intercept is 0. All right, now my y intercept, what's the value of x at my y intercept? Over here, 0 again. Perfect. All right, so I'm gonna again use that to my advantage. So this becomes y equals x squared over x squared minus 4, and if I plug in the x, y equals 0 over 0 minus 4 equals 0, right? So my y-intercept is also 0. Well, that kind of makes sense, because if I have x as 0 into x as 0, then I would also have y over there, right? So it would be 0, 0, comma 0. So my intercept is 0, comma 0. My intercept is x and y intercept is 0, comma 0. That means my graph would cross the over from here like this. All right, now let's look at C. What does C say? Is the function even or odd? Okay, so how do we find the function is even or odd? Also, a function is even when, I mean, it looks like this. So if a function is even, it mirrors its graph on the x-axis. Like let's say a y was the mirror, it would look like this. X squared is a even function, so it looks like this. And odd functions mirror themselves across the x-axis. So let's say like this. These are odd functions. They mirror themselves through the origin. Now, how to find them? Y equals x square over x square minus 4. The way to find that is I have to plug in a negative x inside of this. So let's say this was f of x, and I have to plug negative x inside of this. So f of minus x, this becomes minus x squared over minus x whole squared minus 4. So this becomes x square over x square minus 4, f of negative x. Now this is precisely f of x, right? They both are the same thing. So this would be f of negative x equals f of x. Now mathematically, if you reach this conclusion, even if I plug in a negative x, I get x. Even if I plug in negative numbers over here, I get positive answers, right? So that is when my equation is even. Now let's say, how do we find if something was odd? If I do something like this, and let's say I reach something like minus x square plus 4. If I take a negative common, let's say it was like this, and if I take a negative common, it would be my negative of x square minus 4. So it would be negative of f of x. And if I plug in negative x and it leads to something like that, negative of f of x, like the negative comes out, then the function is odd. And if say let's say we had something like f of if we had x square over x square plus 4 and a negative is outside, doesn't look really like anything we started with, This is neither even, neither odd. So even stays f of x, odd multiplies negative f of x. Neither odd, none of those cases. All right. With this, we know that our function would mirror on the y-axis. Even. Okay. Now D. Find the horizontal asymptotes. How do we find the horizontal asymptotes? If you guys were in college algebra, I would teach you with the shortcut, but don't use the shortcut. You need to know it. Okay? For this, what I have to do is that I have to make my limit go to positive and negative infinity. Okay? How do I solve that? Now, either you can use the, well, it wouldn't always work, but over here L'Hopital rule would work. It would help you to find the infinite limit. But generally, we have the method of look at the highest power on the bottom and divide by that power on the numerator and denominator. So this would become x square over x square over x square over x square minus 4 over x square. Okay? And the limit goes to x to the plus minus infinity. So now this becomes 1 over 1 minus 4 over x squared. Now basically, because it is x squared, I don't really care if it's plus or minus infinity. It's going to make it positive. So this becomes 1 over 1 minus 4 over infinity. 4 over a very big number is just 0. So it makes it 0. Makes it 1 over 1 minus 1. 1 minus 0, which is just 1. So I have an horizontal asymptote at y equals 1. Okay? Alright? What's the next? Yeah, with the horizontal asymptote, let me also tell you the vertical asymptote. So the vertical asymptotes were basically the numbers that were not included in my domain, which were plus and minus 2. So I have a vertical asymptote at plus and plus 2, x equals plus 2 and x equals minus 2. Okay? Now the next is find the all critical points and interval with increasing, decreasing, local min, max, concave, up, down. Okay, let's do E. X square over x square minus 4. Now, how do I find the local min max? I first differentiated, right? Fx equals that. So let me do the first derivative and the second derivative test. So f dash x would be equal to, we have to use the quotient rule over here, and the mnemonic for that is low d high minus high d low over low. So low squared, low. So low square minus 1 d of high, which is 2x, minus high d of low, which is just 2x again, over low. So low squared. Okay? I found this very silly when I got to know about this over here, but it actually works. I remember it. So over here, this becomes 2x cubed. Well, we can keep it like that. No, let's do it like this. So 2x cubed minus 8x minus 2x cubed. Alright, so over x square minus 4. Do not open this on the bottom. Keep it like that. So I can cancel these and these out. Actually, am I sharing my screen? Let me share it fully. Okay. Now these and these cancel out. This and this cancel out. So this not this and this this and this cancel out. So this we have a negative 8x over x square minus 4 to the power 2 remaining. So f dash x. Now we have to find the DNEs and when the equation is 0. So basically equating the top and bottom equal to 0. Let's first equate the bottom equal to 0. X square minus 4 whole square equals 0. Taking an under root on both sides becomes x square minus 4 equals 0. X square equals 2. X equals plus and minus 2. Okay. And these are two of my critical points. Oh, actually, yeah, I remember it now. Okay, we'll talk about this later. And x equals, and we had the top as negative 8x equals 0. So x equals 0. Now let's look at our equation. Do we have positive and negative 2 inside of our domain? We do not. So that's why they are not my critical numbers. Somebody asked me how do we know if they are critical or not. They have to belong to the domain. They are not inside the domain. So that's why these would not be my critical points. Okay? Cancel them out. Like that. Or like that. So the only critical point is 0. Now let me get my equation again, which is negative 8x over x square minus 4 whole square. Alright, now pick a number less than 0. Negative 1. Put negative 1 over here. Becomes positive on the top, and on the bottom, because I have the x, I have the squared over here, it would turn everything positive. So I have positive over positive, which is just positive. And if I plug in something bigger than 0 over here, it becomes negative 8 times some positive value. That's negative, and this always stays positive. Negative over positive is negative. So now this goes, look over here. Well, first we can say that this goes like this, positive, and then decreases. So this should be a local maximum. But you can also look over here. It is positive. So this would be a local max. Okay? Alright. So local max at 0, increasing from on technology. Oh my god. Okay, increasing from minus infinity to 0, and decreasing from 0 to infinity. Okay, looks something like this. We have a graph and looks something like this. Okay, well, it would look something like this, I think. Yeah. All right, because it has it intersects at 0, 0, 2, right? So it should look something like this. All right, now next is concavity. So let me see, is the concavity the next point? Yeah. Okay, next is concave up, concave down, and points of inflection. All right, so our equation was minus 8x f dash x equals minus 8x over x square minus whole square, x square minus 4 whole square. All right, now let's take a derivative of that. F dash dash x equals low d high minus high d low or low low. Or let me show you another perspective. We can also take it like this. F dash x equals negative 8x x square minus 4 to the power negative 2. Exactly same thing. Now we can use the product rule. F dash dash x equals, so derivative of the first one, negative 8 x square minus 4 to the power, and actually this would make it more messy. Never mind. but we can technically do it that way. All right, let me just use the product, I mean the quotient rule. So low d high, low d of high, which is negative 8, minus high d low. High d of low is, oh my god, let me calculate this. X square minus 4 whole square, which is something to the power of 2. Bring the power down, reduce by 1. Alright, what's inside x square minus 4, which is just 2x? So this should be 4x x square minus 4. Alright, I multiply the 2 and 2 over x square minus 4 to the power 4. Don't even attempt to do the bottom part. Okay, let's clean up the top. Alright, let me take one of those factors common, x square minus 4. So this would be x square minus 4. X square minus 4. I'm left with one factor inside over here. Minus 8 minus 8x 4x, and the one factor that was here, it's gone outside over here, over x square minus 4 to the power 4. Now I can subtract this with one of the powers. This just becomes, let me do this too, so becomes negative 8 squared, negative 8x squared. 8 4s are 32 plus 32 minus 8 times 4 is 32 and becomes positive 32x. Wait, is this supposed to be x over here? You know, sometimes I just pray stuff to just cancel out. Low d of high minus high d of low. Well, I guess our prayers have not been answered this time. It's fine. Hey, this is 4x squared. Be very careful with your factoring out and everything. Into x squared. Yeah. Alright. Over x squared minus 4 whole cubed. So this would be 32 minus 8 is 24 x plus 32 over x squared minus 4 whole cubed. Let me quickly check if that's the case. Hey Harry, I have to drive home. I'll try joining in. No worries, Jaren. I have recorded the session. I mean, I am recording this. Well, hopefully the recording doesn't corrupt. But we'll leave that to God. Drive home safe. Let me see if I can see if I am correct. Concavity. Where's the concave part? Yeah, we're going correct. We are going in the right direction. Nice. So this would be, let's take out 8 common from the top. So this would become 3x squared plus 4 over x squared minus 4 cubed. Now we have to do the concavity test. Equate the top and bottom equal to 0. 3x squared plus 4 equals 0. This would be 3x squared equals negative 4. Wait, what? Alright, we can still use it to find the concavity. Alright, a little bit of correction on the tops. They are not points of inflection. but we can still use them to determine if it's increasing or decreasing. So a number smaller than negative 2, that would be negative 3. So negative 3, plugging in negative 3 over here, that would give me positive on the top, positive on the bottom, positive over here. Negative 1, plugging negative 1 over here would give me negative times negative, which is positive. Positive or positive is positive. I mean, it doesn't really change the thing, but it's just that there are separate chunks now. So increasing from minus infinity to minus 2 and union 2 to 0. 0 to 2, sorry, minus infinity to 0, yeah. And then 0 to 2, union 2 to infinity. We have to just mention that they are not in our answers. Alright, now this leads to x squared equals minus 4 over 3, and if we take an under root, this would be x squared equals root minus 4 over 3. This doesn't make any sense because it's a negative answer, so we would reject this answer. The negative square roots are complex, they are not, we can't represent them on the graph. Alright, now equating the bottom equal to 0, we already know this would lead to plus and minus 2, but because these are not in my domain, these would not be points of inflection, but I can still use them to calculate my answer. So minus 2, 2, and they would be excluded. Now let me get this over here. 8 3x square plus 4 over x square minus 4 whole cubed. Now let's pick a number bigger than negative 2. So if I plug in a negative 2 over here, the top always stays positive. So this is positive, but on the bottom, now because I have a cube over here, I have to find it out. So let's pick negative 3. Negative 3 is 9 minus 4, which is 5. So this is positive or positive. This region is positive. Alright. Now, let's pick between negative 2 and 2, which is 0. So this would be positive on the top, and on the bottom I have 0 minus 4 cubed, which is negative. So positive over negative, which is negative. So this region is negative. And from 2 to infinity, which is, let's pick a number 1000. So this is 8 times some positive number on the top, and on the bottom 1000 minus 1000, 1000 times 1000, which is a positive number. Minus 4 wouldn't do anything, so positive or positive is positive. So this is my concavity test. Concave up on minus infinity to minus 2, union 2 to infinity, and concave down from minus 2 to 2. Alright. Now, and we have no points of inflection. Now, after all of that yapping session, we have all the information we need. Alright, what do we know? Let's get our information piece by piece. So we know that our domain is from this to this, and we have vertical asymptotes at 2 and negative 2. We have a horizontal asymptote at y equals 1. We have an intercept at 0 comma 0, and we have our function is even, so it reflects upon the y-axis. We know that we have increasing and decreasing functions, increasing from negative infinity to negative 2, and negative 2 to infinity, and negative 2 to 0 it's increasing, 0 to negative 2 is decreasing, and 2 to infinity it's increasing. Okay, let me actually so if I plug in 0, I would just get 0 because it's an intercept. Okay, let me draw a graph over here, and let me use my information piece by piece. I'm pretty sure they won't make you draw, but it's always good to know. Okay, now let me put my vertical asymptotes. So over here, now don't take my word for it. I don't know what your professor wants. Okay, my professor didn't make me, but yours can. So I have vertical asymptotes at 2, 2, and a horizontal asymptote at 1. I also know that it intersects over here. Okay, now I have a few things over here. So let me make a number line over here. Minus 2, 2, 0, and another one from here to here, which is at minus 2 and 2. Concave up, positive, negative, positive. So positive, negative, positive, and this is positive, positive, negative, negative. Positive, positive, negative, negative. Now I have, oh no, my mom's calling. She'll have to wait. All right. Uh, so I have like this, right? Now, which one of them is concave up and increasing? Over here, these are concave ups and these are concave downs. This is increasing, this is decreasing, this is increasing again, and this is decreasing. Now, which one of them is positive and concave? So I have concave up over here and I have positive, so it should look something like this. So it would be something like this. All right, and I have, next is from negative 2 to 0, I have increasing and concave down. So increasing and concave down is something like this. So it should look something like this. Like this. Okay, next is negative is in decreasing and concave down. So decreasing and concave down is this. So it should look something like this, and I know it intercepts at 0, 0. And again I have decreasing and concave up. So concave up and decreasing should look something like this. All right. Oh. All right. So should look something like this. Our graph. Wanna test it out on Desmos? Desmos x squared, and I would really need to ramp up our progress after this because we have only 1 hour left. All right, looks pretty much the same, right? All right, so now are we clear with this? This was just using the things we already know to plot our graph. Your professor might or might not make you draw the graph, but following the instructions is quite easy. All right, should we move forward to antiderivatives? All right. Moving forward. Oh well, before antiderivatives, we would have optimization. Let's do an optimization problem quickly. So in optimization, basically all you have to do is that you have to make a formula, and there would be a bridging formula with it, and you have to either find the absolute maximum or the absolute minimum. It would be like the local max and min in that case. Okay. So there would be a formula given in which you would want one variable. There would be another formula, another equation, basically one formula that you have to make, one equation that you would have. You would use that equation to bridge both of those variables and get a single variable. You would find the maximum or the minimum of that variable. Once you find that value, you plug that into that original equation, that the relation equation you were given, and you will find the second point. Let's do one of the examples because nothing can be done without examples. So let's do 13th. A rectangle bird sanctuary is, okay, let me do this. Okay. A rectangle bird sanctuary, 300 square foot area, is about to be fenced off against squirrels. Alright. Well, I mean, they can climb up the fences, but it's the math, man. We cannot argue against them. The first thing would be to draw the diagram. Alright, the sanctuary is 300 square feet area. So I've been given the area as 300 square feet. Now, find the dimension that will require at least the least amount of fencing given. So I have to find the absolute minimum of something. Given that the one side of sanctuary is protected by Dr. Miller's house. Alright, so one side is protected by Dr. Miller's house. And I have to find the least amount of fencing. That means I have to find the absolute minimum of the perimeter. Okay, perimeter. Okay, first let's make some variables. So let's make the lengths x and the widths y. Okay. Now, area is x times y, length times breadth, or length times width, which is 300. This is my bridging relation. This is the one relation that makes my both of my variables related. Now, I have to find the absolute minimum of perimeter. What is the formula of perimeter? Over here, it would be modified because one of the sides is already taken by Dr. Miller's house. So, it would be x plus y plus y. This is the perimeter, total length of the boundaries, total length of the fencing. Alright, now we want to make it f of x or y, something like that. We want to make it a function, okay? So I will use this to replace one of my variables. So this would be x plus 2y, and I need to find the area, and sorry, I need to find the p of something that's inside. Alright, so let's I mean, we can pick anything. Let's pick y. So y equals 300 over x. Let's make it like that. So now I can replace it over here. X plus 2 times 300 over x. And now p of x, this is, so basically if I plug in x over here, this would give me the perimeter. Now, what we need to do is that we need to, I mean, let's just first simplify it. And let's find the derivative of this. So we need to find the absolute minimum. How do we find the absolute minimum? The first derivative test. Now, before we begin with that, my distances cannot be 0, right? And that is reflected in this question. So if we look over here, we have to the something to the power 0. I mean, we have x on the bottom, right? And x equals 0. We cannot have that. So that's not in my domain. So make a note that 0 is not included in my domain. Okay? Now this would be x squared plus, or we can just take the derivative as it is, 1 plus, and I can write this as to the power minus 1. Constant stay out, and the negative comes down, reduced by 1. This would be written like this: 1 plus 600, I mean 1 minus 600 over x squared. This would be x squared minus 600 over x squared p of x, p dash x. Now, equating the top equal to 0, x squared minus 400 equals 0, x squared equals 600, and the square root of that is something. We don't really care right now. I mean, we can. 300, 150, 75, 5 is 15, I believe. 75 divided by 5. Yeah, 15, 5, 3, 3, 1. So taking these out, taking these pair out. Okay. 10 root 2 times 3, 10 root 6. Okay. So this is one of my critical points, and my other critical point was x equals 0. And well, this cannot be my x equals 0, cannot be my critical point, but I can use it to find my points of my increasing and decreasing. 0, 10 root 6. Now, can distances ever be negative? We're not talking about physics over here. No, right? So we will ignore this part. And my distance also can't be 0. It was excluded. Alright, so now let's focus on this region over here. Pick a number smaller than 10 root 6. Let's pick 1. If I plug in 1 over here, this 1 minus 600, so that's negative on the top. On the bottom it's positive, so it's this region becomes negative. And if I plug a number bigger than 10 root 6, let's say 1 billion. 1 billion squared minus 600, definitely positive. Positive over positive, it's positive. So this region becomes positive. Now, since this goes from negative to positive, like this, right? This is a absolute minimum. I can also look at this value over here. So it's an absolute it's a local minimum right now. How do we prove that this is the absolute minimum? Now, pay attention, everybody. You need to write this line in your question or you lose point. Right? Because 10 root 6 is the only minimum, local minimum in my equation. Therefore, it is also the absolute minimum. Make sure you write this. Okay? You will lose points if you don't write this, if you don't give a explanation of why it's the absolute minimum. Alright, now x, we had x, right? Yeah, so x equals 10 root 6. We have established that this is one of the sides that is the minimum. How do we find the y? We plug it into the equation that related it. Y equals 300 over x. So that becomes 300 over 10 root 6, which is 30 over root 6. You can leave it like that. Doesn't make any difference. 30 over root 6. Or if you are feeling generous enough, you can rationalize it. Doesn't really make a difference. Totally depends upon your professor. Can make it 30 root 6 over 6, which is should be 50. Yeah, 50 root 6. So y equals 50 root 6. Alright, these are your dimensions. These are the dimension. X is 10 root 6 and the y is 50 root 6. So the longer side is 50 root 6 and the shorter side is 10 root 6. If they ask you to find the perimeter, what the least fencing would be, you can just use the perimeter rule formula you had. X plus y plus y. X plus y plus y. So it's 10 root 6 plus 50 root 6 plus 50 root 6, which is basically 110 root 6. This is the perimeter, the fencing that would be required. Alright, is everybody clear with this? Your first step is to draw the diagram. Second step, find the thing that relates them. Third step, find the function that you need to find the max or min of. Fourth step, find the max or min. Fifth step, very crucial, don't forget to write this line. Sixth step, after you find the max or min of one function, one variable, find the other one using the same relative equation we had that relates both of them. and then you would have your x and y's, and additionally you can just get the thing they wanted, like the perimeter, let's say, if they required it. Okay, are we good with optimization? It's a big number, it's a big name, optimization, but it's not really anything, it's just max or min in disguise. All right, so let's move forward to antiderivatives now. 45 minutes for antiderivatives. Let's see. I hope we finish it. Okay, first, antiderivatives. What are they? So let's like derivative, right? Derivatives were going inside. It was zooming in. Let me go over here. All right. Now derivatives were zooming in. They were finding the slope of the equation at a particular point. Okay, that were derivatives. Antiderivatives is the opposite. It's zooming out. It's finding the area under the graph. Okay, that's antiderivatives. That's integral. That's basically what antiderivatives do. Reverse derivatives, the opposite of derivatives. If the derivative of sine x is cosine of x, the antiderivative of cosine of x would be sine x. Okay, it's going the other way. Now I have a few rules for that, a few formulas of antiderivative and derivatives. You need to memorize these. Let me go one by one. So let's say I have x to the power n. The antiderivative of this would be raise the power by 1 and divide by that power. Okay, simple enough. The derivative of 1 over x, let's say if it's like x to the power minus 1, right? If I use that format, it would be like x to the power 0 over 0. Doesn't make any sense. So the derivative of 1 over the antiderivative of 1 over x is log of mod x. E to the power x stays e to the power x if you differentiate or if you derivate or antiderivate it. B of x is b of x over log of b. Cosine x becomes negative cosine of x. Cos x becomes sine of x. Secant square x becomes tangent of x. Cosecant tangent of x. Yeah. Similarly, cosecant square x becomes negative of cot x. Secant x tan x becomes secant x. Cosecant x cot x becomes negative cosecant of x. And this is arc sine, this is arc tan. Okay, very important. You need to know this, especially people studying from Dr. Miller. This is his favorite function, 1 over 1 plus x squared, arctan. Okay, if you differentiate arctan, becomes 1 over 1 plus x squared. If you want to integrate 1 over 1 plus x squared, becomes arctan. Okay, if you don't know anything in calculus, this is one thing you should know. Okay, can we move forward to some examples? I mean, we should. Okay, let's do some examples. Find the antiderivatives of these. Most general antiderivative. Okay. Well, let me do these after I tell you about the and after each integration to these things. Then it would make much more sense. Let's first do this thing, the area under the graph. All right. Now, what did I say? The antiderivative was the finding the area under the graph, right? Now, just like in derivatives, we had an elementary formula, right? We used limits to find derivatives. We bridged from limits to derivatives for you guys to know what happens. Similarly, over here we have a method to find the area under the graph. Okay, let's say I have this graph over here and I have something like this. Okay, I want to find from here, from here to here. Okay, and let's say I divide my line into, let's say, 4 parts. Okay, 4 equal parts. I'll name them delta x. Okay, and I'll draw straight lines from here. Becomes something like this, becomes something like this, becomes something like that. Okay, not like that, like this, and maybe one more over here, delta x. Now, do you agree if I continue to increase the frequency of these rectangles, I would eventually cover the curvature of the graph, right? So, over here, what we have to do is that we have to find, so these are rectangles, right? The area of a rectangle is length times width. So length over here is this, which is basically plugging in the value of this number. Let's say 1, 2, 3, 4. This would be f of 1 times delta of x, right? Plus f of 2 delta of x, right? Similarly, up to f of 3 delta of x plus f of 4 delta of x, right? This would give me the approximate area of the approximate area under the graph, a very vague approximation. And this would, and I can take the delta x is common outside. This would become f of 1 plus f of 2 plus f of 3 plus f of 4. This would give me my area under the graph. Okay, the more rectangles I have, the more precise my answer would be, the more gaps I would be not the more gaps I would be taking into consideration. Now, how does this work with the question? Okay, let's get rid of this thing first so that we can get into the actual stuff. Alright, so you would have, let's say, a number line and you have 1, 4, 2, 3. Okay, let's say your x is delta is delta x is x2 minus x1 over n. Let's say your x2 is 4, x1 is that, and you need 4 spaces. So this would be 4 minus 1 over, oh no, you need 3 spaces. So this would be 4 minus 1 over 3, which is 3 over 3. So that means you leave spaces of 1. Now this will all make sense eventually. So if I have lower sum, then I have to pick I have to pick 3 positions, right? So I will pick the ones from the left, 1, 2, 3. N is 3. If I, let me just put n equals 3. And if I have to pick the upper bound, it would be 1, 2, 3 from here. If I have to pick midpoints, it would be the middle values, 1, 2, 3. Okay, let's do a question to find what it actually is, because it doesn't make any sense without a question. Okay, 24. I'm getting rid of this first because we need to focus more on antiderivative. This will come in the exam, by the way, this thing. They have at least one question word. So f of x equals 3 plus 3x squared. X starts from 1. x1 is 1. x2 is 4. And your n is 6. The formula for delta x is x2 minus x1 over n. So 4 minus 1 over 6. 3 over 6, which is 1 over 2. So you need to have a gap of 1 over 2, and your x starts from 1, ends at 4. Okay, I need to have gaps of 2. So I can make this 2 over 2, I can make this 8 over 2, right? And I can make this I can 3, 4, 5, 6, 7. 3 over 2, 4 over 2, 5 over 2, 6 over 2, 7 over 2. Look at over here. This is 1, 1.5, 2, 2.5, right? Instead of that, I'm just writing them in fractions so that it's easier. Okay. Now, Let's say you have to find it from the left endpoints. You need to pick 6 values. So you will pick 1, 2, 3, 4, 5, 6. These values. You start from the left. Let's say you need the right endpoints. You pick these 1, 2, 3, 4, 5, 6. These as your values. Let's say you wanted midpoints. You would pick the values from between 1, 2, 3, 4, 5, 6. Okay. I'm going to demonstrate one of them because we are running out of time. So let me just demonstrate left. So this would be my formula for it is delta x times f of 2 over 2. Delta x was basically 1 over 2, right? So delta x times f of 2 over 2, which is f of 1, plus f of 3 over 2, plus f of, let me just mark them, 1, 2, 3, 4, 5, 6, plus f of 4 over 2, plus f of 5 over 2, plus f of 6 over 2, plus f of 7 over 2. Now use your calculator to find this calculation, and you would be left with, let me check my solutions, 24, and the left would be 61.125. So this is the approximate using the left bounds. Okay, is this one clear? You have to just split it into, so whatever the result of the delta x is, it's going to tell us how many intervals you're going to put in a number, and yes, after how many intervals you're going to put your next number, that's your delta x, the spacing. If x equals 2, it's gonna be spaced by 2, right? All right. All right, so let's move forward so that we can cover more of the questions. Let me scroll up over here and let's do some antiderivative questions, okay? Let me just first make you guys clear with the properties of integrals. So an integral should perform the way you want it to. So you can, I mean, not the way, I mean, you could, the distribution, I mean. Okay, so now if you want to get an area from, so this is called the integrand. This means from this point to this point, I want the area under the graph. And let's say I want the area under the graph from the point that it started, a to a. So this point, this area would be 0. Okay, if I want to reverse my bounds in my integrand, I can put a negative outside. This would be a to b fx dx. Now why does this happen? Let's say I have from area from here to here, right? If I want to find the area from a to b, let's say it was plus 5, but if I found from b to a, it becomes negative 5. To counter that, I put a negative outside, so it becomes 5 again. It's all about finding the area under the graph. See, I can put a constant out of my derivation. C times b. Oh yeah, no, the constant don't go outside. Basically, if there's only one constant, if I'm taking an entire derivative of that, basically what happens is that we get c. Let's say we can multiply this by x to the power 0, right? Now we have to increase and the constants go out, and if we increase the power by 1, so it would be x1 over 1, right? So this would become c, and in the bound there would be x from b to a. So this would be c b times x minus a times x. Oh, sorry. C of b minus a. This is this is touching a bit on definite integrals. Basically, whenever you have a constant, it would be this bound minus this bound. Don't really need to memorize that. It's gonna come eventually in definite indefinite integrals if it's coming on your exam. Okay, they get distributed. Plus and minus get distributed. The constants come out, and okay, from there's one more property. A to b, you can split it into we have something like fx dx, you can split it into two parts. So you can make it a to b, a to c fx dx plus c to b fx dx. Let's say I have a graph like this, goes like that. This is a and this is b, and the graph was from here to here. Originally my area was this, but I introduced another variable c. So now all I'm doing is that I'm first calculating from here to here in this, and then calculating from here to here in this. It's the exact same thing. I'm just breaking them apart. Alright, the next is if f(x) is greater than 0, then the integrand would be greater than 0. Okay, let's look at these later on. These were basically the ones you needed to know, and let's do some questions. We have half an hour. Okay, finding the most general antiderivative. F of x equals x cubed plus 5x minus 2. Now, derivative is increase the power by 1 and divide by that power. So x to the power 7 divide by that power plus constants come out. This was 1, increase the power by 1, divide by that power, and if it's a constant, it comes up with an x. Now, whenever you take an antiderivative of indefinite integrals, basically when you are not given the bounds, you must introduce the c, because when we take the, or let's call this like big F of x, when we are taking a derivative of this big F of x, it will lead back over here, and this constant will always become 0. So we can have any number over here. This is just a placeholder for any number, the most general antiderivative. Okay, all of these questions that we have, you need to basically simplify them, and they would lead to you can easily antiderivate them. Pick two questions from this, from 18, for me to do. Which ones do you want me to do? Cube. Okay, let's do cube. Okay, f of x equals 2 over 3, x is on the bottom, plus 8 e to the power x minus 1 over 1 plus x squared. Now, I can break this apart as 2 over 3 times 1 over x plus 8 e to the power x minus 1 over 1 plus x squared, f of x. Now, the antiderivative of this would be this part over here, the constants come out, and the antiderivative of 1 over x, remember, it's log of mod x, ln of mod x. 8 e to the power x, the constants come out, e to the power x stays e to the power x, so it stays 8 e to the power x. And remember, this is the thing I was mentioning. Always remember this. This becomes arc tan x, negative r tan x plus c. Okay, one more quickly. We have 27 minutes. I have to cover this too. Oh, all right, let's do O. F of x equals 2 to the power x, 4 to the power x plus 6 to the power x. Now I can write this as 2 to the power x, 2 to the power 2x plus 2, or maybe 6 to the power x. We'll just write this as 6 to the power x. Okay, now the bases are same, the powers get added up. So 2 to the power x times 2 to the power 2x plus 6 to the power x times 2 to the power x. So this would be, when bases are same, the powers get added up. So 3x plus over here, let's do 2 times 3 power x, the power x times 2 to the power x. Oh yeah, now over here we don't even need to do that. Actually, we can delete this, oh no, delete that, And this would be 2 to the power x times 4 to the power x plus 6 to the power x times 2 to the power x. We can take the powers common. 2 times 4 to the power x plus 6 times 2 to the power x. This would become 8 to the power x plus 12 to the power x. Okay, now we can enter derivative. So this would become 8 to the log ln of b to the power x was b to the power x over log of natural log of b plus 12 to the power x over natural log of 12 plus c. Do not forget the c, they will take a point off. C over here, b to the power x is b to the power x over log of b, natural log of b. Okay, all right. Should I move forward now? We get the point. Just simplify and use the antiderivative thing. Okay, now 19. Which one do you want me to do in 19? Come on, fast. We don't have time. G. All right. G D F. G F D. Let me see. G F D. I'll start with G and let's see if we have time left. Okay. F dash dash x equals 5e to the power x. Let me actually first start with A, because I want this lecture for everybody and for the person who is struggling. Okay, let's say it's A. F dash x equals 8 and f of 9 equals 2. Okay, now we need to go back to f of x, right? So I can antiderivative it. So this would become f dash x would become f of x, and I learned that with the constants they have x with them, right? 8x plus c. Now I have been given this crucial piece of information over here which would help me find the c. So if I plug in 9, I get 2. So let's plug in 9 over there. So 8 times 9 plus c equals 2. 8 times 9 is 72. So 72 plus c equals 2. And c equals negative 70. So now I know my c is negative 70. So f of x becomes 8x minus 70. And this is my f of x. Now, with that understood, we can go with, okay. You good with D? Alright. Okay, let's first do G. G is a good one. F dash dash x. I would limit this the 19 to 8:15 so that we can give 15 minutes to this. The ball question. Alright. F dash dash x equals 5e to the power x. Okay, let's take an antiderivative of that. So that becomes f dash x equals, well, it's e to the power x stays e to the power x plus c. And we have been given that f dash of 0 equals 1. F dash of 0 equals 1. So f dash of 0 equals 5e to the power 0 plus c. I mean, it was 1, right? And this is e to the power 0 is 1. 5 plus c. This becomes c equals negative 4. So I can write f dash of x as 5e to the power x minus 4. Let's take an antiderivative again. So this would be fx equals this, or this stays at 5e to the power x because it's antiderivative. I mean, it's e to the power x exponential minus 4x plus c. Alright, I've also been given that f of 1 equals 2. So 2 equals 5e to the power of 1 minus 4 times 1 plus c. This is 2 minus 5e plus 4 equals c. 6 minus 5e equals c. Okay, so my c is 6 minus 5e. So my final answer is fx equals 5e to the power x minus 4x plus 6 minus 5e. Alright, did everybody understand that? I'm just taking antiderivatives and I am finding the c. Alright. Yeah, these aren't too bad. Let me do one more. Let me do d because uh, it's an trigonometric equation. F dash dash x equals sine x plus 2 cos x. F dash x is 0, f dash is 0, and f dash 0 is equal 3. F0 equals negative 1. Okay, now f dash x equals sine x becomes negative cos x. Yeah, negative cos x plus cos x becomes sine x, 2 sine x. I'm taking the entire derivative, not the derivatives. Plus c. So if I plug in 0 over here, it is equal to 3 minus cos of 0 plus 2 sine of 0 plus c. Cos of 0 is 1, negative 1 plus 0 plus c. So c equals 4. I got from here. So f dash x equals minus cos x plus 2 sine x plus 4. Now let's go to f of x. Let's go one level deeper. So cos x antiderivative is sine x, negative sine x would be there, and sine x the antiderivative is negative cos x. So it would be negative 2 cos x. 4 will become 4x plus c. If I plug in 0, I get negative 1. So negative 1 minus sine of 0 minus 2 cos of 0 plus 4 times 0 plus c. Sine 0 is 0, sine cos 0 is 1, negative 2. 4 times 0 is 0 plus c, negative 1. I add 2 on both sides. This becomes 2 minus 1 equals c, c equals 1. So I'm left with my final equation as minus sine x minus 2 cos x plus 4x plus 1. Alright, this is what we have over here, and this is my final answer. Alright guys, should we move on to the word problem? Alright, no worries. Kirnu, we can do that. These are, okay, let me tell you guys. These are exactly like 19 but with words, okay? Nothing to worry about. These are very simple, don't worry. Alright. Now, from the top of the stage located 80 meters in 80 meters in the air. Whoa, they're high up. Jason, I don't know how to say that last word. Derulo, yeah, throws his mic upward. Sorry, I'm not up with pop culture of in the US. Throws his mic upward with a velocity of 10 meters per second. Okay, now let's construct that. He is 80 meters up high. Does anyone know who he is? Type it in the chat while I'm making this. Okay, that's Jason over there. He threw up his mic up with a velocity of 10 meters per second. And the mic would eventually go down and hit the bottom. Okay, he's some pop singer. Okay. Alright, now I know that my acceleration at all time would be 9.8 meters. Okay, first you need to know, guys, you guys need to know this. This is displacement distance, right? Displacement. If I derivate that, I get velocity. And if I derivate, well, not xt. And if I derivate that, I get acceleration. That's what we knew from earlier, right? Right? Come on, I need to know this. Okay. Now, similarly, if you are at acceleration, if you antiderivate that, you get velocity. And if you antiderivate that, you get displacement. Okay. So we can start from acceleration. So acceleration is always minus 9.8 meters per second, right? Oh, well, they have taken it at 9.8 meters per second. So acceleration is always 9.8 meters per second squared, right? With the velocity of that, so I mean we can take it negative because we are. I mean it totally depends on the system we are taking. So let's say we are taking that this is the positive axis. So minus 9.8 meters per second is our, or maybe 9.8 meters per second. Let's take this as our positive axis. All right, it's 9.8 meters per second. Okay. Now let's take a derivative. Let's take a antiderivative of that. So this would become from at to vt. So it is equal to. I mean vt equals. Okay, 9.8 was a constant, so it becomes 9.8 t plus c. T is what variable I'm taking. Okay. Plus c. Now, have I been mentioned about velocity? Yes, I have. At time equals 0, the instant from his hand, at time equals 0, the velocity was 10. Well, that just means f of 0 equals 10, right? So this would be when v is 0, my velocity is 10. So 9.8 times 0 plus c equals 10. So c becomes 10. So velocity time function becomes 9.8 t plus 10. Okay. Now I have to find the distance of the mic, right? So I have to find the distance function. So we have gotten to velocity. Now we have to derivate this again to find. I mean antiderivate this again to find the displacement. So st equals 9.8. The variable over here, I will have to raise its power by 1 and divide by that power. So it becomes 2 over square over 2 plus 10t plus c. Now what else have I been given? Okay, I've been given that it's located 80 meters high in the sky. That means at time t, right, at time 0, at 0 this distance was 80 over here, right? So I've been given that at time 0 my distance was 80 meters. So I can use that over here. 80 equals 9.8 t square 0 squared over 2 plus 10 times 0 plus c. So this would be just c equals 80. So my distance function now, finally, it is 9.8 divided by 2. Let me do 9.8 divided by 2, which is 4.9 t squared plus 10t plus 80. This is my final answer for A. Okay. Okay. First of all, does anyone have any doubts regarding this? How I got this? Perfect. All right. So let's move forward to B. Oh wow! I don't have the question in the right orientation. Okay, that's good. I hope this recording doesn't corrupt. I would cry if it corrupts. Alright. How long does it take for the mic to reach the ground? Okay. What does it mean by mic reaching the ground? What would be the distance with respective to ground when okay, so this is the ground, right? And this is the positive I'm taking like this. So what would be the distance over here when it reaches the ground? When it hits the ground, what would be the distance? Position has to equal to 0. So I'm saying that I have to find the t when my position is 0. Okay. So s of t I know that 4.9 t squared plus 10t plus 80 equals 0. Let me make that plus. Okay, my handwriting is very bad. Sorry for that. Alright. This becomes that, and all we now need to do is to find the factors and the t. Okay, now mm, you can use the. I mean, splitting the middle term would be very difficult in this case. So just let's just use the quadratic formula. Please know the quadratic formula. In my question, in my test three, me personally, it came. Okay, I had to use the quadratic formula. Know the quadratic formula. You're in Calc 1. You should know the quadratic formula. It is minus b plus minus root b square minus 4ac over 2a. Okay, t or x or anything. Okay, good. It's very embarrassing when I have to teach people quadratic formula in Calc 1. Okay, not embarrassing. It's just that come on, guys. You're in Calc 1. You should know. Or if you didn't know, you know now. Okay. All right. Now let me find the t's. So it's minus b minus 10 plus minus root 10 square minus 4 times 4.9 times 80. Now, don't get scared by this. You don't have to do the calculation. This guy over here can do that for you. You have to just plug stuff in. Back in India, they didn't let us use calculators. This is such a blessing. All right. So let's plug in the numbers and let's see what I'll get with my handy dandy calculator. One of them I have to plus and one of them I have to minus. So let's make two cases in which one of them is plus and one of them is minus. I'm referring to this sign over here. Square root of 10 squared minus 4 times 4.9 times 80. Make sure make me, yeah, all right. Over 2 times 4.9. When I was in the exam, I was like double, triple making sure that my calculator is giving me the right answer. Wow, math error. Let me see. Where did I do it wrong? Calculator, come on, bro. Work this time for me. Times. Okay, let's do times. Times. And on the bottom, let's do times. Come on. If I do this and I do that, delete that. Syntax error. Okay, no. Math error again. Oh, I see why it should be math error. Okay, let's just find the b square minus 4ac first. Okay, 10 square minus 4 times 4.9 times 80. Yeah, that's a negative number. Doesn't make any sense. That's why it was throwing me off. So if I wait, what? B square minus 4 times 4.9 times 80. It doesn't make any sense. Let me consult that with my guide real quick. S of t survive plug into 0. Oh wow. Minus 4 point t squared. Why is it minus? Oh, it had to be negative. There you go. That's why you should take it negative. Okay, take this negative, everybody. Negative, negative. Okay, this becomes negative over here. And this just becomes negative 4.9 t squared. Okay? I mean, I was taking it the other direction as positive. I don't know why it then took it as negative. Okay, but make sure to take the acceleration as negative. Okay, we figured it out. Don't worry, we got this. We are not letting anything ruin this session today. So minus 10. Okay, we have 5 minutes. I have to do this very quickly. And I got 3.1470, basically 34171. And if I do a negative, should get a negative number, I think. Alright, so this would be negative 5.187. Okay, can time be negative? Can you go back in time? I don't want Marvel fans right now. Reality. Can we go back? No. Okay, good. So this is something we reject. This is something we reject. Make sure to take the take your axes according to what they were. I took that as positive. So acceleration is always applied in this direction. That's very embarrassing actually. I took it as negative. I don't know why I took. Never mind. Okay. Yes, no negative time. So my time is 3.1471. At 3.1471, it hits the bottom. Okay, what is the velocity when the mic hits the ground? Okay, so I have t this, right? And just need to find the velocity at this point, and I have the function for that. V equals minus 9.8 t plus 10. V t equals minus 9.8 t plus 10. Right? I have to just plug in stuff. Now that I have found my equations. V of 3.1471 equals minus 9.8, 3.1471 plus 10. And let me first increase the duration by. Can I do more than 5? Okay, I can do only 5 minutes. Okay. This automatically shuts down. Plus 10. Okay. The answer I got was negative 20.84158 meters per second. Okay. So it was going this at this speed in this direction. Negative is basically, so I took this as my positive value, right? So and the mic was going in this direction. That's why we got negative velocity. So, but my answer is this. Okay. All right. Are we clear with that information? Do we now know how to do it? You will take acceleration. You will keep going back. You will keep finding the c's. Once you have all your equations, you just plug stuff in the end. Nothing to worry about. It's exactly like 19. All right. With that, is there anything? So we have like 5 minutes left now. Do we have anything? Any doubts? Anything? What are we getting on the test? 100, 10,000, 100, 100,000. Yes, sir. That's what I like to hear. Perfect. No, not minus 36. Not saying my grade because it's bad luck. Oh, look, if you try hard enough, it's not that bad. You just need to. Look, getting better at math, right? It's not about like you are by default are good at math. You, um, yeah, the more practice you do, the more better you get. All right. I used to hold like 5 hour sessions when I was in Calc 1 for free for my classmates. I used to have so much fun. This was so much fun for me today. Thank you guys for joining so much. Thank you so much. And Calc 1 is very fun. All right. Thank you so much. Thank you so much, guys, for the positive comments. No worries, no worries. And let me do a filthy plot in of my workplace. I work at the STEM tutoring center, which is at Sports Arena. And let me just share my screen real quick. Mm-mm-mm-mm. All right. All right. So if you go to Instagram, you can go to GS. Don't look at my feed. GSU STEM Center, and you will basically find the STEM Center over here. Here is where I work, and we have many amazing tutors over here. I work here too, and if you need any help, you can come over there. I can help you further. I am there on Mondays 3 to 5, Tuesdays 11:30 to 1, no, 11:30 to 3. Yeah. And on Wednesday I'm from 2 to 5. So yes, can you do a session like this on final exam? Okay. I'll ask my I'll convince my boss, and I'll do a 4 5 hour session if possible, and I'll record it. I mean, I'll do it with you guys. I'll do my best, okay? I don't promise anything, but we'll see. Okay? No worries. No worries. I love doing this. I love doing this. One of my passion things. I see people are having fun with the whiteboard. You can do anything, just don't draw anything bad. What was sharing? The board, I mean, it's a default board. I don't use it. I use my own thing. I use OBS to do my everything. Alright, let me stop the recording now. Alright, everyone say bye to the recording. Good.